So let us start with discrete mathematics. Okay. So to begin with, let us look at some of the concepts on set theory. Yeah. So the concept of set appears in all mathematics, right? So let us see the notation and terminology of a set theory, which is a basic and used uh, throughout these problems, right? So let us have a closer look on the definitions of a set and elements and subsets. Okay, a set um, may be viewed as well-defined a collection of objects, right, and called the elements or members of the set. Okay, and usually they're written in capitals. It is A, B, or X, Y, Z, and so on. Okay, and in the lower cases, so which is A, B, X, Y, Z, right, to be denoted as the elements of the set. And a synonym of set are class, collection, and a family. And the membership in a set is denoted as A belongs to S. Okay, so or A comma B belongs to S, right? For the set S, right? And this symbol belongs to is an element of that set. Okay, so there are essentially two ways of to specify a particular set. One way, if possible, it is to list its members separated by commas or contained by braces. Okay, and let us see the two ways here. So A, if you consider a set A, okay, so this is 1, 3, 7, 5, 7, and 9. Okay, and if I consider B, okay, X such that X is an odd integer where X is greater than 0. Right? So if you look at this, it consists of numbers, right? A set A consists of numbers, and the second set is which is a set of X such that X is an odd integer where X is greater than 0, is a typical member of a set where X is a member of a set. And yeah, so these are the two ways of representing it or illustrating it. Yeah. Now let us move further. Yeah. Okay. As we move further, now we'll see on subsets. Okay. So suppose every element in A, as set A, is an element of a set B, then we suppose A belongs to A, implies A belongs to B. Then A is a subset of B. Okay, And we also can say that A is contained in B, or B contains A, and the relationship is written as A subset of B, or B is this. Okay, so the two sets are equal if they both have the same elements or equal elements, right? So that is A equals B, right? If on only if A is subset of B and B is subset of A. Okay, so let us look or consider an example. If I consider a set A which has the elements in it, uh, 7, 8, and 9, okay, and another set of elements which is these, and we have one more set. Okay, so then you can see here C is a subset of A, yeah, and C is subset of B also. Okay, since 1 and 3 uh, are the elements of C and also a member of A and B. Okay, they are the member of A and B also. Okay, but B is not a subset of A. Okay, since the elements of B, okay, 2 and 5 does not belongs to A, and similarly A is not a subset of B. Yeah? Great. There are special symbols. Some sets will occur often in the text, and so we usually use special symbols for them. Some such symbols are that is n, capital N, the set of natural numbers. Okay, numbers, or the positive integers 1, 2, 3, and so on, and Z, which is the set of integers. Okay, so they are -2, -1, 0, 1, 2, and so on, and we have Q, that is a set of rational numbers. Okay, and we have R, which is a set of real numbers. Okay, and we have C, which is a set of a complex number. Okay, so if you would observe this, N is a subset of Z, is subset of Q, is a subset of R, and a subset of C. Yeah, and also we'll have a look at the universal set, empty set. So all the set uh, under investigation in any application of a set are assumed to belong some fixed large set called the universal set and is denoted by U. Okay, and uh, for example, if I have as a set, right, S, okay, given an universal set and a property P, okay, so there may not be an element of U which have any property P. For example, the following uh, set has no elements, that is S, okay, X, such that X is a positive integer. Okay, X square is equal to 3. So such a set with no elements is called the empty set, or is denoted by phi or a null set. Okay, so if S and T, if S and T are both empty, then S is equal to T. Okay, so uh, so empty set is also regarded as a subset of every other set. So thus we have this the following simple result, which we state formally. Now let us look at disjoint sets. Yeah, disjoint sets, right? So two sets which considered as A and B, okay, said to be disjoint if they have no elements in common. Suppose if I consider A, uh, which is 1 and 3, yeah, and B, which is 4, 5, and 6. Yeah? So if you look at this, A and B are disjoint. Okay. So since they have no elements in common. Now further, let us look at Venn diagrams. Okay, a Venn diagram is a pictorial representation of a set in which sets are represented by enclosed areas in the plane, right? And the universal set, which is U, is represented by the interior of the rectangle. So let me represent that universal set, and this is A and B. Yeah. Now here, this is a Venn diagram, right? So if A is, if you look at this, this A is a subset of B. So the representing the entire area, and here we have a universal set, and these are the sets which are disjoint, and okay, so yeah. And further, let us look at arguments and Venn diagrams. Okay, many verbal statements are essentially statements about sets, and can therefore be described by Venn diagram. Hence, Venn diagram can sometimes be used to determine whether or not an argument is valid. Okay. Now let us look at set operations here. Yeah. So we'll be studying about basic operations of union, intersection, and complement. Okay. Now start with, let us look at union. Okay. The union of the set A, denoted by A union B, okay, is the set of all elements which belong to A or B. That is, A union B is equal to X, such that X belongs to A or X belongs to B. Okay, here OR is used in the sense of and or, right? So if you look at the Venn diagram, yeah, A and B. So this is completely shaded. Okay, so this is A union B, which is shaded. Now, if you look at intersection, right? So intersection of set A and B, denoted by A intersection B, is the set of elements which belong to A and B, that is A intersection B is equal to X such that X is X belongs to A and X belongs to B. Okay. So if you look at the Venn diagram here, this is A and this is B, and so A intersection B is the shaded one. Okay. Now, if you could recall, the sets A and B are said to be disjoint or non-intersecting if they have no elements in common. Okay, so A intersection B, which is an null set, okay, or the empty set. So if you consider S as A union B, and A intersection B is an null set. So let us consider let A as 1, 2, 3, and B as 3, 4, 5, 6, and C as 2, 3, 8, 9. Right? Now A union B will be 1, 2, 3, 4, 5, 6. Right? Now A intersection B will be 3. Okay, and A union C, if you consider that, so just 1, 2, 3, 8, and 9. Okay, A intersection C, this is 2 and 3. Okay, now let us look at a few examples on complement and differences and symmetric differences. Okay, first let us see the definition of complement. Okay, so which is written as A complement, right? So X such that X belongs to U and X does not belongs to A. So under consideration of particular time or subsets of the fixed universal set, the absolute complement or simply complement of A is denoted by A complement, is the set of element which belongs to universal set but which does not belongs to A. Yeah, and A uh, uh, which is written as symmetric, right? So A B, right? Symmetric difference of A and B is denoted by A by this, right? Consists of those elements which belong to A or B, but not to both. Right? Okay. Yeah, or we can write this A union B. Okay. And now let us see the algebra of set and duality. Okay. Now, the sets under the operations of union, intersection, and complement satisfy various laws and identities that are idempotent law, associative law, commutative, distributive law, identity law, okay, and complement law, and De Morgan's law. So duality, that is, if we consider the principle behind the arrangement, suppose E, and the dual of E is E star of is the equation obtained by replacing each occurrence U in union and intersection. Okay. Okay. Union and intersection, or universal and null set. Right? Uh, okay. Which is intersection, union, and a null set and a universal set. Now let us see power of a set. Power of a set S. This is this set S. A is called the power of set S, and which is denoted as P of S. Okay. So if S is finite, then so is P of S. So in fact, the number of elements in P of S is 2 raised to n power n of S. That is n of S and n of P of S is equal to 2 raised to n of S. So let us see the example. Right? Suppose let us consider the set S, which is 1, 2, 3. Then power of a set, which is P of S, is the elements null set 1, 2, 3, and 1 and 2. And this is 1 and 3. This is 2 and 3. And the whole set itself. So this will be 2 cube, which is 8. 8 elements.